Challenge Senior Kangaroo from 2021. Let's just get straight into it. It's quite a difficult paper, I thought, actually. But anyway, this guy was born in 2015, this person 2018. Minimum number of days between them. Let's shorten the gap between them to just 1 year. And when I say 1 year, I mean actually 1 day, right? You can be born in 2 different years and only be 1 day apart. Right, it's not 2 days because you're going either side of a year. It's just the 1 day apart. This person is 1 day younger than that person. And now what we need to do, because this is a whole minimizing problem, is just insert 2 extra years here to make this 2018. So we just insert 2 lots of 365, 2 years in the middle, and then add the extra 1 day that we had originally, and we get 365 plus 365 plus 1 to give us our answer. Except, and this is probably why no one got this question right, I would imagine, in the real challenge. It turns out 2016 is actually a leap year. And so you actually have to insert a year into here. February the 29th or whatever it is existed in 2016. So this is actually a 366 day long year. So we add 1 year to the total. These are the rules for a leap year, by the way, just in case apparently you need to know that for a senior maths challenge. I certainly would have got this question wrong and just left the answer there and not even considered it at all. But anyway, question number 2. I probably would have also got this question wrong because this is hard. I might quickly show you what I did to start with, but even though it doesn't work. I thought about adding these numbers up, right? So I thought a smart way to add these numbers up is to just add 6 to 36 up and then add in all of the 2000s in afterwards. Now to add up this to this, I can do the formula for adding up numbers, which I think most people who are doing senior Kangaroo sort of know, which is if you're adding up numbers up to n starting at 1 with just a 1 difference, you can just use this formula. So to add up from 6 to 36, all I'm going to do is use this formula with 36, which starts at 1, so then I'll just take away the numbers from 1 to 5, so using this formula with 5. So there's the sum of the numbers up to 36 starting at 1, take away the sum of the numbers up to 5 starting at 1, and that gives me this thing. And then I can, I guess, add in the 31 copies of 2000 as well. Now there are 31 copies, just be careful, there aren't 36 copies here. Sorry, or 30 copies is maybe something that a lot of people would say. There are 31 copies because the 2006 kind of adds, that's almost like starting at 0, and then you have 1 to get to 2007, and then it's 30 from there. Okay, so well, I did some shuffling around here to try and make this easier for me to do. I factorized out some stuff, and it just didn't really work. I was really proud of myself for doing all this. I mean, this halved is 18, which is what I've done there. This I can work out. This I can work out pretty easily. I was pretty proud of myself for doing all of that. And then I worked out that it was not going to be good because it doesn't actually want what the sum of the numbers is. This is the sum of the numbers. It doesn't want that. It wants the sum of all the prime factors. And if you know anything about number theory, and I'll link a video in the description below, finding prime factors of very large numbers when those prime factors themselves are large is really painful. So I just did some bus stops. I divided it by 3, by 7, by 13, by 11, by 17, and nothing was working. I couldn't find a single prime factor without getting any bigger than that. So I thought, okay, there must be a different way in doing this, and there was. But I'm just trying to get across the point here that although I get all of these questions right in the video, that doesn't necessarily mean that I'd walk into the test and get them all right on the thing. Like, I'm not perfect. And you don't need to blame yourself or be harsh on yourself when you can't do these questions. Like, I just ran into a dead end here, and I just wanted to make that point. This is question 2, and I ran into a dead end, right? So, it happens to everyone. It's okay, we just need to rethink our ideas. And what I rethought was, okay, a different way of summing numbers other than this idea, which I immediately went to, a different way of summing numbers is, that's actually what the mean is. The mean of a list of numbers is the number that you may as well just add up instead lots of times and you'll get the same answer, right? So the mean of these numbers is 3, also the median, but that's kind of irrelevant. The mean is 3, so therefore I could just add up a load of 3s and I would get the same sum as adding up these. So when I add up these numbers, I may as well just be adding up a lot of the means. And this is, as soon as I worked out what the mean of these numbers was, I knew I was getting this question right. Because the mean of these numbers is essentially, it's the median as well, because when you have a list of numbers that just goes up by 1, the mean and the median are the same thing. The mean of these numbers is 2021. And you know that you're onto the right track because this is the 2021 challenge. So you know that you're doing something well here. Likewise, just like before, there are 31 copies of 2021 being added up here. So you can, I maybe said very clearly here. There are 36 numbers from 1 to 36. Take away the 5 numbers you need to get to 6 itself, and you have 31 numbers left over here. So there are 31 numbers of 2021 here, so you times them by 31, and this is much easier. It still wants me to work out the prime factors, but this is prime, obviously. I still need the prime factors of this, and the only advice I can say for this now is, when you're doing Senior Math Challenge or Senior Extension Math Challenge Kangaroo, go into that challenge knowing the prime factors of the year that the paper is. So you should have gone into this challenge knowing that the prime factors of 2021 were such and such. Now, of course, I didn't do that because I'm an idiot. So I had to find some way of working out what they are. And what I noticed is that 2025 is 45 squared. I just kind of know this, which was very useful because it's very close. All I need to do is take away 4, which is the same as taking away 2 squared. And then this is a difference of 2 squares. And so I get prime factors of 43 and 47. You should just go into the exam knowing what the prime factors of 2021, or if you're watching this in prep for 2022, know that 2022 is 2 times 1011. 1011 is 3 times 337. So if you're prepping for 2022 now, I think the prime factors of 2022, though I've done it very quickly, are 2 times 3 times 337. But don't quote me on that. Work it out, use a calculator. Go into the exam knowing the prime factors. Anyway, finally, to finish off question 2, which has taken forever, we just need to add these up and we'll get our answer as this 3-digit number here. I should have mentioned at the start that this challenge is different because it's not multiple choice. All the answers are 3-digit numbers. So 121, or in the first question, the 3-digit number was, what was it? 732. It's not multiple choice, it's always 3-digit numbers. If the answer is only a 2-digit number, you just lead a 0 beforehand. So it's like 008 if you needed the answer 8. Anyway, for this question, just get a pen and paper and do it. I mean, if you know something about Eulerian paths, then you can use that idea. But just try drawing it and you'll work out that this is the one that you can't do very easily, and you can't do it at all. In fact, the others you can do pretty easily, to be honest. It only takes a couple of seconds of effort, really. If you want to know the proper thing, I'll put another video in the description below this about Eulerian paths and how to work them out. Essentially, if you call these sort of points where lines either end or join other lines, and you call those nodes, to make an Eulerian path, which is a path you can draw without taking your pen off paper, you can only have at most 2 nodes with an odd number of branches. So if we count here, this node here has 1 branch because it just has 1 thing going this way. This is 4, this is 4, this is 1. That's only 2 nodes with odd numbers, so this is fine. This is 1, 3, because it's 1 this way, 1 this way, 1 this way, and then 3, 1. That's 4 odd numbers, so this is not going to make an Eulerian path because it's got way too many odd nodes. The logic there is that to get all the way around a path, you need to enter and leave a node, right? So to get all the way around this, I would need to enter this node and leave it, because otherwise I'm just going to get trapped here. But of course, entering and leaving is a dual process. It's 2 things. So if you've got nodes with only an odd number of things, you either have to start there, and so you don't enter it at all, so therefore you have an odd number of times that you deal with it because you just leave it, or you end there for the same reason. So this is fine because I can start here and then just leave it once and then do all the normal things and then end here, but this isn't okay because I can't start and end at more than 2 places. Cool, okay, and then these work for the same reason. Question number 4, I know we've got through those first 3 questions quite slowly. It does get nicer and easier from here. Question number 4 is a bit like question number 3, which is if you have awareness of the thing that you're looking at, it's much quicker. It's talking about a right-angled triangle with semicircles drawn over the edges. Now, usually when we look at right-angled triangles and we do a bit of Pythagoras, we look at squares coming off of the edges, and we learn that Pythagoras means that this square plus this square is equal to the area of this square. Now, actually, Pythagoras works for any shape that you draw onto the triangle, the right-angled triangle, as long as those shapes are obviously similar to each other. So you can't use square, triangle, semicircle, but you can use semicircle, semicircle, semicircle. And the area of this one plus the area of this one is still the area of that one, which is really nice because they've just given me the areas of the semicircles. And it's told us that these 2 are the smaller ones. So I just literally have that x squared plus 3x is 180. And this is a very simple quadratic that I'm hoping that we can solve. You just need to have awareness that you're allowed to do that, I guess. X equals minus 15 isn't okay because that makes that a negative area. So the answer is x equals 12. And it says what's the error of the smallest one. Well, 12 squared is 144, 3 times 12 is 36, so the smallest is going to be 36. The answer is 036, because you have to put it as a 3-digit number, so it's just 036. 5, another nice question. Maybe to deal with this, let's just pretend 2021 is n, because that actually shows you that the algebra works out very nicely. This obviously doesn't matter. We can write this in the normal quadratic order, factorize it. This is n plus 1 squared. You can sort of cancel this with this. Technically you need a modulus sign, but it doesn't matter for this question. You just get n plus 1. N was 2021, so the answer is 2022. What's the largest prime factor of t? Well, actually I just did this a few minutes ago. Maybe that's why I was able to do it so quickly. I'm such a liar. Anyway, prime factor of this, divide by 2, divide by 3, and you get 2 times 3 times 337. Very useful if you're prepping for the 2022 challenge, that those are the prime factors of 2022. Please bear that in mind, maybe. The largest prime factor is, of course, 337. Number 6. Okay, so we draw these graphs and we'll count the regions. I've drawn the x-axis bold because that is a region that is a line that is splitting regions, whereas the y-axis does not. So okay, we draw this graph. This is a graph with roots at root 2 and minus root 2, and it's an upside down quadratic, y-intercept of 2. So it looks a bit like, I've drawn this one first, y-intercept of minus 1, roots at 1 and minus 1. I guess that's logical. Y-intercept of 2, roots at root 2, which is a bigger number than minus 1 and plus 1, so it's over here. How many regions does this split to? Again, we use the x-axis to count, so this region is different to this one, so that's first region, second region. Then we have this region is all the same thing because the y-axis is not being used to split regions. That's just a third region, fourth region, fifth region, sixth, seventh, eighth, all here. And then ninth and 10th, because that does split. And we have 0, 1, 0 in total. Again, 3-digit number, lead with a 0 if you have to. Number 7. So we have 5 cards with these numbers on the front, and we have different numbers, different positive integers on the backs. And it's asking us to work out which card has the largest other number on the other side. So clearly this is the largest number on this side, but we're looking at for which is the largest number on the other side. Okay, we have these rules to work with. Now we need to just be logical here about different positive integers. If b and e are positive integers, then c is bigger than b and e, because when you multiply positive integers you just make a bigger number, except for the case where one of the numbers is 1. 1 times 5 is still 5, you don't get bigger, except you have to be different positive integers. So if one of these was a 1, then the other one would be the same as c, and that's not allowed. So c is definitely bigger than b and e. Here, same kind of logic. D is definitely bigger than A and B because these are all positive integers. When you add positive integers, you get a bigger positive integer. So D is definitely bigger than those two. And likewise here, you could rewrite this if you wanted to do as A plus D equals E, and therefore say E is bigger than E and A, and D and A, if you wanted to, but you come up with that. And now we look at these statements and we say, okay, C is bigger than B, and it's also bigger than E, but E is bigger than A. So we can come up with this sort of chain. C is bigger than E, which is bigger than A, and C is bigger than E, which is bigger than D over here. Sorry, so E is bigger than D, which is then bigger than A. Okay, so E was bigger than A, but there's a D in between them. And now B is less than D, so it's somewhere over here. Don't really care. The largest one is C, A, B, C, so that's on the other side of 103. Okay, number 8. The geometric mean is defined. Oh, it actually defines it for you. Okay, hopefully you probably maybe knew what the geometric mean was going into this because you maybe do stats in the A-level stats part of maths. So the geometric mean of 4 numbers is if those 4 numbers are A, B, C, D, is the 4th root of A, B, C, D multiplied together. And the geometric mean of these ones, if they're called E, F, G, H, is the 4th root B, G, F, G, H. And we're looking for the geometric mean of all 8 numbers, which is not going to be the 4th root anymore because there are 8 numbers, so it's going to be the 8th root of A, B, C, D, E, F, G. So okay, how do we work this out? Well, we can multiply these things together. Because they've got the same surds, they're both to the power of a quarter, essentially, we can just multiply underneath the surds, and we end up with that. Now, of course, if we multiply these two things, we multiply these two things. You could multiply those if you wanted to, or just notice 2 to the power 10 you should know is 1024, so this must be 2 to the power 11. This is clearly 2 to the power 3, so multiplied they make 2 to the power 14. Now we're looking for this. This is to the power 1/8. This is to the power 1/4, so if we just raise this to the power of a half, we'll make it into a power of the 8th. So raise that to the power of a half and we get 2 to the power 7, or you can think of it as square rooting both if you want to. 2 to the power 7 you can work out is 128, so the answer is 128. Very useful to know your 2 to the powers of, I think, for math challenge. Question number 9, so these regions all have exactly the same area. Now that's important because we can work out this area here. The radius of the small circle is 2. So this area here is a quarter of the circle, so it's a quarter times pi times 2 squared. 2 squared is of course 4, so this cancels and we get pi. So this area is pi. So this area is pi, so this area is pi, and also so is this and this and this, because that's the same as this one, and so is this and this and this, because that's the same as this one. So every little area here is pi. So what we can say is, well, if we're looking for the slightly bigger radius out to the second circle, that's made up of 1, 2, 3, 4, 5, 6, 7, 8 lots of these areas pi. So pi times little r squared, the area of this second circle, is just 8 lots of pi. Cancel out the pi's and we get r as 2 root 2. Same deal for the bigger circle, which I'll call big R. Pi times big R squared is 1, 2, 3 times 4, so that's 12 of these areas. It's going to be 12 pi divided by pi root for 2 root 3, and it's asking us the product of the 3 radii is y. Now the radii are 2, 2 root 2 and 2 root 3, so multiply those together to make 8 root 6, and then y squared is going to be squaring this. To square that we just square the first thing, which is 64, square root 6, which is 6, 64 times 6 is 384, and that will be our answer. 10. A dealer bought 2 cars. So let's just make a table here for paid. Let's say that he paid A for the first car and B for the second car, because that's actually what it says later here as the ratio. Now if he paid A for the first car and he sold it for 40% more, as a decimal multiplier that's 1.4A. Paid B for the second car, sold it for 60% more, that's 1.6B. The sum that he paid is obviously A plus B, and the sum that he sold is 1.4a plus 1.6b, but it's also apparently 1.54a plus b. So we have here that this plus this must equal that. Of course we can expand out, we can simplify, we can, I don't know how I dealt with this, times everything by 100 of course, yep. And now there is an infinite number of solutions to this, but whenever you see this, the easiest thing to do is just set a to be 6 and b to be 14. Just opposite them, because 6 times 14 equals 14 times 6. So set a to be 6, b to be 14, cancel it down, and we have our simple ratio of 3 to 7, so that's our a and b. What's the value of this, just randomly? Well, 11 times 3 plus 13 times 7, just work that out, I guess, try not to stuff it up, and you get the answer of 124. 11, so we're halfway, I think, which is good. We have a dice. I think I had been teaching I can't even remember the sample spaces. I've been thinking about sample spaces, I think, in lesson time when I first did this challenge, when it first came out. So that's how I did it with sample spaces. I just said, well, 1, 2, 3, 4, 5, 6, 4, 4, 4, 5, 5, 5, and I literally just wrote out all the answers to the game. So this person wins if the number is bigger than this one, draws if they're the same, and so on. You can write this much quicker than I am. You can shorthand it by just making this a whole W column rather than writing W 6 times, whatever. But all you need to do now is just count up the probability that Niles wins. Niles has this die, so the probability that Niles wins is 1, 2, 3, 4, 5, 6. Just count them up. You get this. There are 36 numbers, of course, because it's 6 times 6. Simplify that down. So that's P, and that's Q. And then 7 times 7 is 49. 11 times 12 is this. They're just asking you to work that out, and you get 181. There are probably better ways of doing that. Maybe there aren't, though. Maybe that's what sample space is for, isn't it? I know it's like year 8 maths, but don't be too snobbish, just do it. It's fine, it works well. Question number 12. There are lots of balls in a crate, balls are numbered, and we work out the digit sum. So you just sum up the digits and you have 2021 has a digit sum of 5. She colors, or she notes that balls with the same, with equal digit sums have the same color. So basically every ball that has a digit sum of 5 has the same color, and every ball with a digit sum of 4 has the same color, which is a different color. And saying how many colors are there? Well, the smallest digit sum you can have is 1, because the ball labeled 1 has a digit sum of 1. So the smallest color you can have representing is this digit sum 1. Now, of course, more balls will have this color. The ball 1000 will also have a digit sum of 1 and be the same color, but that doesn't really matter. What's the largest digit sum you can have? Well, it's probably this, right? Add those up for 28. And so it seems pretty obvious then there are 28 different colors. I haven't shown that. I haven't shown that you can get every color in between here. I haven't even shown this is the largest one you can get. But you only have an hour to do this challenge. It actually might be an hour and a half. I can't quite remember. Don't waste time trying to prove stuff like that. This seems very logical. This seems like it will be the highest. It seems like you'll be able to get every number in between because you can just lower this by 1, lower this by 1, and you get keep going. So let's just go with 0 to 8. 13. So it's going to do a product table here, a multiplication table. What's the sum of all the odd ones? Well, the only way to make an odd digit in here is to do odd times odd. That's the only way to make an odd when you multiply. So we're going to do 1 times 1, so this one, and then 1 times 3 gives us this one, 1 times 5 gives us this one, 1 times 7, and 1 times 9. Those are going to be all of the odds in that row. And we just want to add this up. Then this row doesn't have any odds because you're not doing odd times odd, you're always doing even times something. So even here times something here. So that's not going to have any odds. The next row will be 3 times 1 will be odd, 3 times 3 will be odd, 3 times 5, and so on. The 5th row will do it, the 7th row will do it, and the 9th row will do it as well. Now, instead of working these out, what I'm going to do is I'm actually going to factorize the 1 times out of all of these things. So rather than saying this is 1 times 1 plus 1 times 3 plus 1 times 5, it's actually 1 into this. Because of course if we expand this, we get 1 times 1 plus 1 times 3 plus 1 times 5, and so on. So I can factorize this one in the same way, I can factorize this one in the same way, and the two in between. I can also just do this sum now. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 9 is 25. This is 1 times 25, this is 3 times 25, this is 9 times 25. We've still got the 5 and the 7 rows in the middle here. So we're going to do 1 times 25, plus 3 times 25, plus 5, plus 7, plus 9 times 25. And this is just 1 lot of this, plus 3 lots of that is 4 lots of 25, 9 lots of 25, 16, 25 lots of 25 is going to be the answer, which is 65. Quite a nice question, I thought. So we have a super complicated graph, I assume here, meets the x-axis that many places, y-axis that many places. We essentially just need to find p and q, because then we could put them into here. So to find when a graph meets the x-axis, you just set y to be 0. When a graph meets the x-axis, it's not got any vertical or distance, it's on the x-axis, it's not going up or down, so y is 0. Just put y as 0 into here and solve this equation. Now of course we can expand this out if we want to. You can divide by x squared, but notice when you do that, you're going to have a solution x equals 0. So if you just put x is equals 0 into all of this, you get a solution, 0 equals 0. If you put x is 0 into this, you don't, you get 4 equals 0, which isn't okay. So that's why you can't just divide by x squared without noting solution at x equals 0. Now we can solve this, it's just a quadratic, and we don't really need to solve it, right? We just need to note at this point, we're going to get 2 more solutions. There'll be root 8 minus 2 plus minus root 8, that's 2 solutions. So we have 3 solutions here in total, so p is 3. And we do the same thing with the y-axis. We say when it intersects the y-axis, that means x equals 0. But x is equals 0 into this, it actually ends up being slightly easier. Take away y to the 4 both sides, and the only solution to this is y equals 0. And so we only have 1 solution there, so q is 1. 100 times 3 is 300, plus 1 times 100 is 400, and that'll be the answer. 5, so when you're doing these kind of questions, just run through it. Just pretend the first one is true, run through. When you end up with a contradiction, you start again, you say first statement is false, you go through it, and you just try and find a system whereby everything agrees with each other. So let's just say that this statement is true. That of course means that this statement is true because that's literally what it says. Now this statement must be true, which means 206 is false, but 206 isn't false, right? 1 plus 1 is definitely 2. So we've got a contradiction, which means we go back to the start and we say, okay, that one must be false then. So if this is false, then this statement is, so this is saying this statement is true, but it's not a true statement, so that means that this statement is false, which is good, because if this statement is false, that means 206 is true, which it is, which is good. So we go back up to the top and we say, okay, statement 201 is true. Well, we know statement 201 is false, so that's also a false statement. Statement 202 is false, well that's a true statement, because we've got it right there. And then none of the statements, this, or this are true. Well, that's actually false because this one is 204. But it doesn't matter because it's just saying which is the lowest numbered. But this all now agrees with each other. There's no contradiction anywhere. So I'm good to go. Which is the lowest numbered statement, which is true? 204 is the lowest. These are all false, so 204. 16. I really liked this question because I really like polygon angles and polygons. Don't know why. I obviously really like number theory for reasons that I don't need to explain. So I really like this question. You could use the interior angle formula for this, for a polygon. I never use this formula. This is, by the way, for a regular polygon, isn't it? Which I maybe should have said. But actually, if you're dealing with regular polygons, much easier to use the exterior formula. 360 divided by the number of sides is the exterior angle. Much easier to use. So, okay, how am I going to use this? Well, if the interior angle needs to be a decimal or a half integer, which is an integer or a decimal part of 0.5, then so does the exterior angle, right? Because it's just 180 minus that thing. So I can just think about exterior angles instead of interior ones then. So, okay. 360, therefore, divided by some number n, has to be an integer or have a decimal of 0.5 as its decimal thing. So, okay, how do I get that? Well, if I break 360 into its prime factors, I get this. And now, how do I have this? Well, the idea here is that if n was 7, if I had 7 sides, then there'd be nothing on top for the 7 to cancel with, and you just end up dividing a number by 7, which will give you a horrible decimal with sevenths in it. So I obviously don't want that. But if n was a 5, if I only had 5 sides, this would just cancel with this 5. You'd be ending up with this, which is just a whole number, right? I think it's 72. I don't know. Probably 72. So, yeah, it is, because 360 divided by, yeah. So the idea is, I want this number n just to have enough to just cancel these things out. I don't want to have anything extra. I just need it to cancel with these things at most. It doesn't have to cancel with them. N could be 1, right? And then we'd end up with an integer up here as well, so that's good. So, okay, I could use any n that has at most 4 2s, 2 3s, and 1 5. Now, the reason I'm saying it can have 2 3s in it is because it can't have 3 3s, because then you cancel both of these and you still have a 3 on the bottom to divide by, which will give you a 0.33. So it can have 2 3s and have 1 5 for the same reason. Why can it have 4 2s? Well, because if it has an extra 2, then that's just where you're going to get the 0.5 from. So if it was just 2 to the power 4 on the bottom here, you'd cancel 3 of them, and you just have 3 squared times 5, which is a whole number, divided by the last 2 left over, which will give you the 0.5. So I'm allowed to have the 4 2s. So now all I have to do is count how many numbers have at most 4 2s, 2 3s, and 1 5 in their prime factorization. Except actually, that gives you 5 choices for the 2s. And now we're getting into the number theory stuff, right? Because when you're counting these up, you can count numbers that don't have any 2s in them at all. So actually your number can have 0, 1, 2, 3, or 4 2s in it. When you're doing this combinatorics thing and counting how many 2s you actually want, you can have 5 of them now, because you can have 0 2s. Likewise, you can have 3 3s, and you can have 2 5s. Either 0 of them or 1 of them. You can't actually have 2 5s. You've got 2 choices for the 5s, I should have said. So we do 5 choices times 3 choices times 2 choices for 30 choices in total. So that is almost the answer. Not quite there. There's a sting in this question, which is you can't have n be 1, because you can't have a polygon with 1 side, and you can't have n be 2 because you can't have a polygon with 2 sides. The least number of sides a polygon can have is 3. So we take 2 away from that and we end up with 0, 2, 8. Quite a tough question, I thought, but also really fun. I'll put a video in the description talking a bit more about prime factorization, number of choices and stuff like that. So if you're interested in going through more of that, then please watch that video. Okay, so find the remainder of Q when it's divided by 1,000. Okay, now the first thing to look at is this number here. 2 to the power 21 is just 10 times 2 to the power 221, which is this, I guess. And this is just a number with 1 with 21 zeros after it. So this whole number here is just going to have 21 zeros at the end. I don't care what the front number is, but it's going to have 21 zeros at the end. So when I divide by 1,000, this is not going to participate, because the remainder is 0 when it divides by 1,000, because it's got way too many zeros anyway. So I can actually just ignore the middle part. I can just get rid of it and look at this part here. Now this clearly has remainder 202 when divided by 1,000, so that's fine. What about this? And I thought about this for a while, trying to find some intelligent way of doing it. I couldn't. What I eventually just decided to do was work it out. So clearly 10 plus 10 plus 1 is 21, so I can do this. I know this is 1,024. I can double this up, and now I could just work this out, or I could think, well actually, this is just 1,000 plus 24 times 2,000 plus 48. And when you expand these brackets, just like we discussed with this number, like for example, this expansion is going to have too many zeros at the end. It's going to be 48,000, which is going to have zero remainder divided by 1,000, and likewise these two, and likewise obviously these two. So actually all I care about are these two. Like what's the remainder of those two? Do that multiplication, get this, and so the remainder is 152. Divide by 1,000, remainder 152. So the remainder of this is 152, remainder of that is 202, and we have the answer of 354. Good, only a few questions left. I thought I'd do something a bit different for this question. I have a method for doing this question, but I didn't really like it, and I actually just got sent in a better method by by a mathematician that I know in real life who's very, very good. And I liked his method more, so I just decided, as a bit of a change, to just put his method on the screen, and I'll talk through someone else's method for once, because wouldn't that be exciting and just a bit different? So okay, some years like 2022 have the property that they only use at most two digits. So this number is only using the digits 2 and 0. So okay, how many years between this have this property? So I'm essentially looking to discount any number that has 3 or 4 digits in it. I only want at most 2. It can have 1 digit, because that counts as at most 2. It can have either 1 digit or 2 digits, but not 3 or 4. Now, what he's written really small in here, I'm sorry you can't see this, is every number up to 99 has at most 2 digits, right? A number up to 99 can't have 3 digits for obvious reasons, 3 different digits. So there are 99 numbers up to the number 99 that don't have at most 2 different digits. So he's written this 99, and that goes into his total later. Then he starts considering the 3-digit numbers. So okay, you've firstly got the numbers that just repeat the same digits 3 times, like 333 or 666, and there are 9 of those. Notice you can't use 000 because that's doesn't start at 1, so you can have 9 of those. Then he's looked at the numbers that have 2 digits, either going repeat different, like 221, or repeating first and third, so 212. And he said there are 9 choices for the first digit, because remember you can't start with a 0 if it's a natural 3-digit number. If it starts with a 0, you're just counting the 2-digit numbers, which you've already done. So it can't start with 0, so you've got 9 choices for that. And you've got obviously just the 1 choice for this, because it has to be the same as that. And then you've got 9 choices for this, because although you can use a 0 here, you can't use the digit you've already used. So it's 10 minus 1, which is 9. So, and then you just times together to make 81. And then there are 3 different layouts for this. You can either have the unique one here, or unique one here with the 2 repeats there. So it's 81 times the 3 to make this, plus the 9, and then that's his total for the 3 digits. So this is the total for the 1 and 2s, this is the total for the 3s, and now he finds the total of how many 4 digits only have 1 or 2 digits. And again, he starts with just the same number over and over, 1111. There are 9 of those. Then he has a different number at the end. So there are 9 choices for the digit you want to repeat 3 times, and then again 9 choices for the thing at the end. 9 times 9 is 81. But there are 3 ways of doing this, right? You can either put the single digit here, the different single digit there, or the single digit there. So there are 3 ways of doing that. There's actually also a single digit here, which is actually separately written down here. So a small increase in efficiency of his method here would be to just make that an 81 times 4 and discount this, which is just having the different one at the front here. So anyway, but he's just counted it differently, that's fine. Then he's looked at the case where you've got 2 digits twice, so 2244 or 4455. And you can do that by either having this set up, and again 9 times 9 is 81, or you can shuffle these around and do same and just say XYXY or XYYX. And there are 6 ways to shuffle those around. I might put in a video about what this 3C2 means a little bit, but there are only 3 ways to shuffle that around. There's both Y's at the front, Y at front and end, and then both Y's back. Only 3 ways. Add those all up, add them to the total, and you get 927 as your final thing. Quite a nice method. Quite enjoyed explaining someone else with this method for once. That was quite nice. And anyway, question number 19, let's go back to my work. So f of x is defined to be this. So that means f of x squared, you just input x squared instead of the x's. So you get this. As soon as you see this, you factorize difference of 2 squares. Never not been helpful when you see this. And it turns out to be helpful because when you write this out, f of x squared is this times f of x is just that. Of course, this just cancels with that. I've written 0.72 as 72 over 100, and you'll see why in a second. You get this. You can simplify 72 over 100 to be this, that's why I did that, cross multiply, and you just end up with a quadratic. It's not a very nice quadratic, but it is a quadratic. It does actually factorize, although it's quite hard to see, and you have solutions at 7 and 1/7, which seems not very good. A is bigger than B, so A would have to be 7 here. Until you see this, and you realize you need to times the B by 7, and then you go, so I have got this right then. Great. 19 times this one plus 7 times that one, that's going to be a 1, and you get the answer. Good. I really like the function questions. I think they're really good. If you're just practiced at functions, I think you should be able to get these questions all the time, which is good. It's a nice question. So they always like to finish these exams with a cross number nowadays. I don't mind that too much because I think they're okay. So okay, let's just do this very in order. 1 across, so that's this one here. A prime, which is the sum of 2 squares. So I wrote out the squares, and then I looked for primes that were the sum of 2 of them. So 1 plus 4 is 5, which is a prime, except these are non-zero digits, so I can't do 0, 5. So I'm looking for 2 digits. Okay, so 4 plus 9 is 13, that is prime. And I just kept doing that. It took me a little while to make sure I'd got all of them, but this was my list that I came up with. 3 is twice the 3 across is twice down to 2 down. Well, I don't really have much to go on there, so I'll just leave that for now. 1 down is p times q, where they're prime, so I'll just list the primes really quickly, or at least some of them. P times q, where p and q are prime, and the difference between the primes is 4. That's really important. So it's not 2 and 3, because then 2 isn't 3 plus 4, or vice versa. So it's stuff like 3 and 7, right? Where the difference is 4. So 3 times 7 is 21, so that's one of my options. And actually, when you go through this, the only other option is 7 times 11, which is 77. You can't use 13 times 17 because that gives you a 3-digit number, and 1 down is a 2-digit number. So these are the only choices. That's actually a really good way to, a good place to know that you've made progress here, because that's quite restrictive, so that's good. Okay, now where do we go? Well, let's look back at this. 3 across is twice 2 down. So when I double 2 down, I get 3 across. Now what that means is this number must be below 5. Because if this number was 500, it's not, because you can't use non-zero digits. But if you double anything bigger than 500, you end up with a 4-digit number. So this must be below 5. So that's quite useful. But also this number here, for exactly the same reason, or similar kind of ideas, this number doesn't have to be more than 5, because you could double 100 to get 200. But it has to be more than 1. I can't double a 3-digit number and end up with a 3-digit number that starts with a 1, right? The smallest 3-digit number I could double is 100, which gives me 200. So this has to be bigger than a 1. But of course, my only two options for 1 down are 21 and 77. So it can't be 21. This must be 77. So okay, this starts with a 7. We've got 7 going across here. So what would this have to be to double to make this? Well, it looks like 2 down would have to start with a 3, right? It has to be between 350 and 400. So that's cool. So therefore it starts with a 3, right? 400 actually doubles to 800, so it starts with a 3. Good. So this number is 73, and just double check. Oh yeah, 1 across, 73 is one of my options there. So that's good. I haven't broken that rule there. That's good. So it does start with a 3. Okay. Where else can I go? Well, this is probably the most challenging bit of it. But when you double this number, you get this number, as I said a few times. But think about what happens when you double something like 350. You're going to get something like 700, but look at this digit here, it's shared. The second digit of this number is the same as the second digit of that number. So when I double something like 360, I get 720, and we don't share the digit. 90 doubles to 780, we still don't share the digit. The only way to share this middle digit is to double something bigger than 395. That's the only way to end up with something that also has a 9 here. That's the only way to do it. And again, quite a lot of thought went into getting to that result. That seems like it comes out of nowhere. You just got to hope that you have some time at the end of the exam to actually think this through. But this has got to be a 9, because this number can only be 395 or 396, 397, 398 or 399. Which is it? Well, to work that out, we need to use the last piece of information here. 4 down is 60% of 5 across. So if this number was 395, this number would be 790, which it actually can't be because we can't use zeros. So this could be a 396. If it was a 396, then this would be 792. Right? So that digit would start with a 2. Now, this is a two-digit number. In this case, this is a two-digit number that starts with a 6, and this is one that starts with a 2. Now, that doesn't suggest that this number is 60% of that number. 20-something is not 60% of 60-something. So this doesn't seem very hopeful. Next is a 7. 7 doubles to 14, so that number would be a 4. That does seem good. 70-something, 40-something could well be 60% of 70-something, right? That seems very helpful. Next would be an 8, which doubles to a 16. That seems too big for 60% of that. If a two-digit number with 60, that seems too big. And of course, 9 and 8, that's far too big. This is the most hopeful. And in fact, it's the only one that works. A bit of logic would help you out with that. So for example, if you say this is 80, 50% is 80, or 60% of 80 is, I think, 48, which is still way too small to get to the 60. So this seems like by far the best option. You can verify if you want to. You can work out that indeed, if you choose a 5, then 45 is 60% of 75. Now, actually, you don't need to work that out because it only asks you for 2 down, which is 397. You actually don't need this answer here. The answer is 397. So yeah, quite a tough question there at the end. You need to really think it through quite hard. Quite a tough paper, to be honest. The entire thing I thought there was some tricky. It opened up with those first 2 horrific things. But anyway, thank you so much for watching, and I'll see you next time.